Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this lecture on advanced transition metal organometallic chemistry. In this lecture today we are going to start discussing with the molecular orbital correlation diagram of bis arene transition metal complexes, and then look into the reactivity of these compound based on their molecular orbital or electronic structures. Now, in our last class we have discussed on the construction of this molecular orbital picture for these transition metal bis arene complexes. In particular, we have looked at the molecular orbital correlation diagram for bis benzene chromium complex, and what we had seen is that these correlation diagram is quite similar to that of the metallocene correlation diagram, particularly of ferrocene that we had discussed in our earlier lecture. So, all of these correlation diagram in gist gives us the electronic structure, the electron filling of their molecular orbitals, which can also explain the magnetic as well as chemical reactivity of these bis arene transition metal complexes. So, to begin with, from where we had left in the last class, we had finished the construction of molecular orbital correlation diagram for the bis benzene chromium complex, and we had seen that the several ligand based orbital remains non bonding, in the sense that they do not engage in any atomic orbital on the metal side, and these non bonding orbitals are A to G as shown over here in green, and then E to U seen over here in green, and these two B1U and B2G remains non bonding, in the sense that they do not interact with anything. So, these are the benzene bis benzene atomic orbitals which remains non bonding and does not interact with the ligand orbitals. Similarly, from the metal counterpart, the A1G metal d orbital remains non bonding, as can be seen over here. Also, the p orbital A2U, one of the p orbital, remains non bonding. So, the orbitals which remains non bonding are shown over here, and the rest of the orbitals they engage in bonding. The 18 valence electron that compounds have goes up to A1G filling, that is the sigma. So, that 18 goes around 2, 4, this is 8, 12, 2, 4, 6, 8, 10, 12, 14, 16, 18. So, this is how the 18 orbitals are filled. And one last thing about previous discussion is the fact that the time of kind of interaction one exists, this E2G engage in delta type interaction, A1G engage in sigma interaction, and E1G star engage in pi type interactions. So, these are the three interactions sigma, delta, pi type which are prevalent in bis benzene chromium of D6 symmetry. Now, I would sort of dwell upon little bit on the differences as well as similarities of this bis benzene as well chromium as well as bis cyclopentadienyl iron complexes. For example, bis benzene chromium, this is in eclipsed geometry, and this is by far the most stable one as seen from the X-ray structure, whereas bis cyclopentadienyl iron this is in staggered geometry, these are again the probably the more stable conformation. The point group over here is D6H, over here it is D5D, and then the similarity is that both are 18 valence electron compounds, both are 18 valence electron compounds. As far as the metal to ligand bonding is concerned, metal to ligand delta bonding is more predominant in this as well as compared to the bis iron complexes. So, C6H6 M back bonding more significant, as compared to comparatively this is more as to this kind of makes sense or kind of quite intuitive, given the fact that benzene is a neutral ligand. So, electron donation from metal onto a neutral ligand is probably more feasible as opposed to cyclopentadienyl anion, where it is already anionic in nature, and hence the back bonding of electron donation from metal to already electron rich anion is kind of going to be less prominent. So, that is a significant difference. Also the bond energy, the benzene chromium bond energy D Cr C6 H6 is less 170 kilojoule per mole, whereas in ferrocene DFeC5H5 the bond energy is 260 kilojoule per mole. So, now this Cp this is more strongly bound D Fe C5 H5 is 260, whereas D Cr C6 H6 equals 170. What on the face what we see is that this is a weaker bond as compared to this cyclopentadienyl ferrocene, and that also is quite intuitive given the fact that cyclopentadienyl anion is a negatively anionic ligand, and hence it binds more strongly to the electron deficient cationic iron species, giving rise to more stronger bond having higher bond dissociation energy, whereas arenes being neutral ligand, they bind less tightly to cationic metals, and as a result this bond dissociation energy is quite low. And another important thing about this base the bis arene complexes in general is that these bis arene complexes are quite air sensitive, whereas the metallocenes most of them are air stable. For example, over here bis chromium is air sensitive, whereas the corresponding the metallocene counterpart bis iron is air stable. So, we had made a sharp parallel compare and contrast between the bis one representative example of bis arene complexes in the form of this 18 electron bis benzene chromium with that of another 18 electron bis cyclopentadienyl iron complexes, and what we found that there are certain similarities for them as well as there are certain differences. The similarities being that they both are 18 valence electron compounds, the differences being that the chromium bis benzene is air sensitive, iron bis cyclopentadienyl is air stable. The chromium bis benzene exists in an eclipsed geometry, which is the most stable conformation, whereas iron bis cyclopentadienyl compound exists in a staggered geometry. Also the back bonding is more predominant in bis benzene chromium as compared to the back bonding or delta interaction in iron bis cyclopentadienyl complex. And lastly, the bond energy of arene metal bond energy is less as compared to the cyclopentadienyl metal bond energy in the metallocene. Here is a sharp compare and contrast between a representative example of a bis arene transition metal complex and that of these bis cyclopentadienyl iron transition metal complexes. Not only the bis arene, the chromium is air sensitive. Almost all of the known transition metal bis benzene complexes are air sensitive. The example being C6 H6 whole 2 titanium, C6 H6 whole 2 vanadium, C6 H6 whole 2 niobium, C6 H6 whole 2 chromium, C6 H6 whole 2 molybdenum, so on and so forth. So, all of these are almost extremely to very air sensitive. to great extent. Okay. Now, another spectral feature of these bis arene complexes involves the structural characterization of bis chromatin complexes, and which has shown that the ligand to ligand distance in eclipsed bis chromium compound is 322 picometer, and chromium to the edge of the ring is 213 picometer. Also, there is an interesting example in which 19 electron bis hexamethyl benzene derivative of rhenium can be prepared from the 18 electron counterpart. There is a nice example in which bis benzene rhenium, a 19 electron unstable compound, can be prepared from the bis benzene rhenium 18 electron counterpart, and being unstable it dissociates immediately to form a dimeric compound. The equation is given over here. So, this is C6 Me6 hexamethyl benzene to rhenium PF6. This is a 18 valence electron complex in presence of lithium at 200 degrees centigrade, and then the depositing in the cold finger at 77 Kelvin. This very intriguing 19 electron complex C6 Me6 whole to rhenium is isolated. Now, this is a 19 valence electron compound which is isolated at very low temperature of 77 Kelvin, and then at room temperature it decomposes to give this dimer. C6 Me6 whole to Re, which again is a 18 valence electron compound. Okay. So, another interesting feature about these bis arene complexes are their reactivity, and one important aspect is that they are very air sensitive and prone to oxidation. So, all neutral bis arene metal complexes are air sensitive and vulnerable to oxidation. And this is something which is quite sharp in contrast to that of ferrocene or the metallocene complexes. Many 18 electron metallocene complexes are quite stable in air and moisture, and not as much susceptible to oxidation as the current bis arene complexes are. And this tendency to overcome oxidation is achieved by replacement of hydrogens with electron withdrawing group can overcome vulnerability towards oxidation. Example, eta6 C6 H5 Cl equal to chromium is air stable. The next important reaction are these ligand exchange reactions. And in the ligand exchange reactions, just simple B-serine transition metal complexes are kinetically inert towards ligand exchange, whereas condensed arenes which has multiple cyclic arene rings fused together, they are more labile towards ligand exchange reactions and can be exchanged. So, this is an interesting observation. For example, this benzene chromium is kinetically inert. Whereas condensed arene ligands are labile. And can be exchanged. For example, as is shown over here, whole to chromium plus 3 bipyridine at 25 degree centigrade gives chromium plus 2 C10H8. Another interesting example of this is shown over here and has been successfully used for synthesizing mixed benzene naphthalene dinuclear complex. I will illustrate this with this beautiful example in which bis benzene naphthalene chromium complex in THF in presence of benzene at 100 degree centigrade in a sealed tube gives this beautiful mixed benzene naphthalene dinuclear complex and naphthalene dinuclear complex, and this exploits this ligand exchange ability of condensed arene chromium complex. So, this is a nice work in which this mixed benzene naphthalene dinuclear complex can be observed. Another interesting feature about these arene complexes is that unlike the metallocene counterparts, the bis arene complexes does not undergo electrophilic aromatic substitution reaction. So, this also is a prominent deviation from the chemistry that we had observed for bis cyclopentadienyl transition metal complexes. The fact is that bis arene metal complexes do not undergo electrophilic aromatic substitution reactions. Substitution reactions similar to metallocenes, and as attacking electrophiles oxidizes the central metal atom. So, this is a interesting deviation for bis arene complexes in terms of chemical reactivity with regard to that of bis cyclopentadienyl transition metal complexes. So, with this I would like to draw a conclusion on today's lecture. In this lecture we have started off by looking at the electronic structure of bis benzene chromium complex, particularly with regard to the molecular orbitals that are engaged in the overall molecular structure, resulting in their electronic structure. We had also seen how these electronics molecular orbital filling led to their chemical reactivity and property. We have also drawn a parallel for bis transition metal arene complexes with regard to bis cyclopentadienyl transition metal complexes in terms of their total valence electron counts, reactivity, then bond energy in terms of the extent of metal to ligand back donation occurring in these complexes. We have looked into some of the key features that arises out of these electronic structure of these bis-arene complexes, and we have looked into reactions like oxidations, then ligand exchange, as well as electrophilic substitution, aromatic substitution reactions for bis-arene transition metal complexes. So, with this I would like to close today's discussion on the reactivity of transition metal bis-arene complexes. Some more discussion still remains on this reactivity talk that we are discussing, and would like to conclude that in the next lecture. So, I would like to again thank you for being with me in this lecture, and I look forward again to initiate this discussion in the subsequent lecture when we take up the reactivity of bis-arene transition metal complexes in bit more detail. Till then, goodbye and thank you.